Hello everyone, welcome to day 66 of Learning Data Science. And in my previous video, what we have done, I've explained you about R square and adjusted R square. We discussed about the linear regression, cost functions, and all those things, right? So today, what's the agenda of today's? So today we will be going to discuss about ridge and lasso. What do you understand by ridge and lasso regression? Ridge and lasso, ridge and lasso. We are going to discuss about that. So before that, what you have to understand is what we have to discuss is this is our line, right? Sorry, this is our graph, and this is my x. X is basically the data points, right? This is my data points. And basically, in linear regression, right? In linear regression, what we are basically doing, right? Okay. This is my data point. And upon this x in linear regression, we are predicting y. Okay. So for example, I have a data points for say here is my one data point, and here is my another data point, and here is my another data point. Okay. So basically I'm having three data points, and if I will try to draw the best fit line. So how does the best fit line will look like? Okay, how will so this is my what? This is my best fit line, right? This is my best fit line. So in linear regression, we are trying to find the best fit line, right? And for example, okay, uh, this was my this was my predicted points, okay? And for here in the orange, what you can see, this is my actual data points, right? These are my actual data points. The dots and the cross are my predicted points. Okay. So for example, here some value of x will be there, right? Here also some values of x will be there. Here also some values of x will be there. So upon these x values, we are predicting what will be the value of y. So what is my y? What is my y? My y is my nothing but my output, right? And what is my x? X is my input. X is my input, right? And Y is my output. Why we are predicting it, and upon how we are predicting it, by the X. Okay, with the help of the data points. Okay, so for example, we have made our model, everything is good, and now some new data points comes. Okay, so for example, new data points is somewhere around the X is here. Okay, this is my new data point, my new X. So ultimately, what Y will be trying to do? Y will be trying to predict the value on the change. So somewhere around the value will be here, right? Here, the value will come here, right? So what's happening here, right? My line is not performing good with my new data, right? So if you can recall with the machine learning concepts, which we have been following or you have been following, okay, so what's the concept behind it? Whenever our data doesn't performs good with the predicted points and with the testing points, right? So in short, what you can say, the test data and actual data, right? So with my test data, the model is performing good, you can see. But when I have given my actual data, the model is not performing good. So in this case, what is this case? This case is called overfitting. What is what it is called? It is called overfitting. Again, in overfitting, what it happens, our model performs well with test data, but it doesn't performs well with sorry, uh, our model performs good with our training data, but it doesn't perform good with our test data, right? So for example, here my training data, in my training, okay, the accuracy, for example, the model accuracy is 90%, right? When this happens, this is happening when I am training my model with my trained data, right? So my accuracy is 90%, right? And when we are testing our model with our test data, so in test, say the accuracy is coming somewhere around 60%. So whenever these things will happen, it is called overfitting model. Okay. And with respect to bias and variance, okay. So you have to understand it. Whenever we are using a term called training, every time we use it for training, we use bias name. For training, we use bias, and for test, we call variance. We call it variance. And whenever my model is performing good, my accuracy is good, then what we call is at low variance. We call it low variance. Sorry, it's with respect to training, so it will be low bias, right? Whenever there is a bias, you should know that our training data is involved there, right? And whenever test is written, what we do, we call it as variance. Variance is involved, right? So again, you can see in my testing, right? Accuracy is not high. So it will be high variance. High variance. Okay, whenever we are using the term test data, in that we are denoting it by variance. And whenever we are using training data, we are doing it by bias. So whenever my training data gives is more accurate, then the accuracy is more, then we call is at low bias. And if my accuracy is high, or sorry, if my accuracy is low, then we call it as high bias. With respect to training and with respect to test, its variance. So whenever accuracy is more, we call it low. Whenever accuracy is less, we call it high. And for training, we call bias, and for test, we call variance. So just understand these two things. So we have two conditions whenever we are building any model. First, we have discussed about overfitting, right? And the next, what we will discuss about underfitting. So you have understood in our overfitting model, okay, in our overfitting condition, our model performs well with our test data, but it doesn't performs well with our training data, right? So in my underfitting, in my underfitting, in underfitting, what happens? In underfitting, my training data, my training data, suppose has a accuracy of 60%, right? And my test data, and my test data has accuracy of somewhere around 59%, right? 59%. So with the respect of bias and variance, how do we donate it? Okay. What do we call it? In underfitting model, what happens? You can see training. So I have told you whenever there is a word called train data, so you should use bias, right? So you have written here bias. And whenever there is a test, you have written here variance. You have written here variance. And again, I have told you whenever my accuracy is low, so it will be high. We call it high bias. We call it high bias. And also you can see in my test, the accuracy is low. So what do we call? We call it as high variance. So there is one question for you. What is a question for my ideal data set? for my ideal data set, the bias and variance, what it will be. Okay. Obviously, the answer will be low bias and low variance. Why? Low means high accuracy. Bias means training data. So for training data, I'm getting highest accuracy, as well as for test data, I'm getting highest accuracy. So the term highest accuracy denotes with low, and with test data, it, it determines with variance, right? So for our ideal model, every time we should have low bias and high variance. Low bias and low variance. That is our ideal model, right? So in Ridge and Lasso, what we are going to discuss it. Okay. So I hope you have understood about overfitting, underfitting, and also you have understood about uh, what do we call it as high bias, high variance, low bias, low variance. What is the ideal condition for our model to train? Okay, what it should be. Okay, so let's take, I will again draw a graph here, right? And suppose this is my best fit line, okay? And here is my data points. Okay, here is my data points. So what, this is my predicted points, right? And what is my actual points? My actual points is here in the red. My actual points is here, right? So how do we calculate this? We have already discussed about the cost function, okay? So what is a cost function? Obviously, it's 1 by 2m. M here is basically number of data points from I is equal to 1 till m, and h theta of x, h theta of xi minus yi whole square, right? This is only our cost function, okay? And what is this basically called? H theta of xi minus yi. What is this? This is nothing but the distance of the error, sum of residuals, sum of residuals. We have already discussed about that sum of residuals. This is nothing residual. This is nothing. This is nothing but the distance between these 2 points. This is my h theta of xi. What is this? This is nothing but my predicted point, and this is my actual point. So actual point minus predicted point. Only this thing is there, right? So for instance, okay, let's consider only this, which is under bracket, right? So if we will write here h theta of xi, for instance, we are only considering the value which is under bracket, right? Yi, okay. And this h theta of x, this h theta of x is the predicted points. And what is the predicted points? How do we calculate it? Okay, right. So we have already discussed there in h theta of x. How do we write it? We write it by theta naught plus theta 1 of x1, right? So this basically, this theta 1 is nothing but our slope, right? This is nothing but our slope. And in this case, just assume, you can see here my points are overlapping. So ultimately, what it will come? It will come 0. At the end, our value will be 0. And what does cost function does? Cost functions basically help us to reduce the error, reduce the distance between predicted points and actual points. So what's basically the cost function is doing? So we are getting here 0. So ultimately, if for one value, the value will be 0. Similarly, for every, ultimately at the end, you will get a value as 0. So you would think that our model is 100% accurate. Okay. So whenever you get this, that your model is 100% accurate, that means your model is overfitting conditions. You shouldn't get your accuracy as 100%. Just keep these things in mind. Whenever you are getting accuracy as 100%, that time your model is overfitting condition. That means your model is performing well with the training data, but it will not give results with the test data, right? So to avoid this situation, what we are doing, we are basically here adding lambda, and we are doing here slope square. We are doing here slope square. So, for example, what is the slope of this line? What is the slope of this line? And basically, how we determine the slope of this line? By differentiating it. And also, we can determine the unit change in x, how it's going to affect y, that only the slope. So, for instance, I'm just taking a random value, okay? It's not that a value is given and this will be the universal value. No, it's not like that. For instance, I'm taking lambda value as 1, okay? And slope value, I'm taking it as 2, okay? So what it will come, it I will execute it, it will be somewhere around 1 into 2 square, right? And somewhere around the value will be 4, right? So what we are getting it at the end, we were getting the sum of residuals, the cost functions. It was under overfitting, and we were trying to just improve our model from overfitting case. And with the help of lambda and slope square, right? What we did, we have done here slope square, and here you can see our value had come from 0 to 4, from 0 to 4. And at the end, what you have to do? At the end, you have to reduce this value. At the end, you have to reduce this value, right? So, for example, okay, uh, let's take another line is there, another best fit line is there, okay. Another best fit line is there, and suppose this line is this. Suppose this line is this. Another best fit line is there, right? And what happens if you would check it? If you would check it, the slope of this line will be slightly less than this slope. Why? Because it is tilt. If it is like this, you can see the slope will be maximum. If it is tilt, the slope will be less. So somewhere around, initially it was 2. So now just let's take, it will be again, if I am tilting it, okay? If I am tilting it, so my lambda value is 1, okay? Uh, my lambda value is 1. And instead of initially my slope was 2, and now, for example, it is being reduced to 1.2. From 2, it reduced to 1.2. And the distance between these 2 points, the distance between these 2 points, the distance between these points, the distance between these points will be not much, right? It would be a small value. This distance will be a small value. So what it will happen here, we are adding some small value, with this thing, with slope, and slope is generally my 1.2. So what will be the answer of this? So it will be somewhere around, okay, somewhere around, if we'll do this, so it will come 1.44, it will come 1.44, or somewhere around, it was initially it was 0. So now let's take 0 0.8. So somewhere around my value will be 2.04, 2.05, 2.02. Okay. So somewhere around my value will be 2.02. So ultimately, what you have seen, we have reduced the value, and with the help of this best fit line, what we are our overfitting condition will be solved. If we are adding some new points, if we have to predict this point, so what will happen? It will show you somewhere around here, the point will be here. So ultimately, the distance, if you will calculate, it will give the best solution for this particular line rather than the initial line. Okay. So in ridge, what we call is ridge, we also call it as L2 regularization. L2 regularization. In ridge, we called L2 regularization. Okay. Now we will discuss about lasso. Okay. What do you understand by lasso? So there is a slight change in lasso, not very much. Okay. What is the slight change? In ridge, you have understood this is my s theta of x minus yi minus y. Okay. So instead of slope, what we are going to do, we are going to do the mod. We are not squaring it, but we are taking the mod of our slopes. Okay. We are taking the mod of our slopes. So this is basically lasso. Lasso. And lasso, we also call it as L2 L2 regularization. And lasso, it also helps you in feature selection. Lasso also helps you in feature selection. Feature selection. So you will just say how it helps in feature selection. Okay. So if we have learned about in linear regression, multilinear regression, okay, what were the predicted points? What were the our this h theta of xi? Okay. What is this points? What is this points? This points is nothing but theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, right? So my theta 1, theta 2, theta 3, these all are nothing but the slopes, right? And whenever, if my slope, this slope value is very, very small, so what it will happen, these features will be ultimately neglected. We are adding here slope. What we are going to do, we are adding here slope, we are taking the mod, we are taking the mod, and ultimately we are summing up these things. And if the value of slope will be very, very small, so our feature will be neglected, right? So here it comes to end of lasso and ridge regression, right? So for tomorrow, we are going to start with next machine learning algorithm. And here we have completed with linear regression. Everything we have completed it. With respect to linear regression, R square, adjusted R square, ridge and lasso, we completed everything. Tomorrow we are going to start with the new. Till then, just subscribe my channel or you will not get the notification of when I'm uploading this. Okay. And when is my live sessions so that you can just join my Zoom sessions and you can ask the doubts. Okay. So till then, goodbye, take care and Jai Hind.